Now let's take a look at how we can compute some very simple but very useful properties of binary images. Let's assume that the binary image shown here is continuous. We'll talk about discrete binary images later. Let's also assume that for our purposes here, there's only one object in the binary image. So you have bxy, that's your characteristic function, which is 1 on the object and 0 outside. X and y are the spatial coordinates. So the simplest property you can compute is the area of the object, and that's the 0th moment. You simply take b, integrate it over the entire image, you have the area. Useful property because even the area alone can be used to distinguish between a small number of objects. Now, if you wanted a robot, say for instance, to go and pick up the object, you need to know its location. And an easy way to define the location is the center of the area, which is the first moment. So how does one compute the first moment? It's x times b integrated over the entire image divided by the area. And it's y times b integrated over the entire image divided by the area. That gives you x bar and y bar, the x and y coordinates of the center of the area. This is very much analogous to, in mechanics, the centroid of an object. If you have an object like this, it has uniform thickness, made of the same material, its centroid, the location of its centroid, or center of mass, corresponds to the center of area shown here. So there are analogs to all of this in mechanics. Now the question is, how do we define the orientation of the object? If you want the robot to go and pick it up, you need to know not only where it is, but how it's oriented, so you can go in and grasp it. This is difficult to define, because if you're looking at this object here, you might define the orientation as perhaps the axis that's passing through the two most distant points, or the dominant line. You can pick an axis in many different ways. We want to do this in a principled way, which is easy to compute, and it is something that can be robustly determined irrespective of the position and translation of the object. So for that, we're going to use the second moment. We're going to define the orientation as the axis of least minimum second moment. What does that really mean? There exists an axis around which if you spin this object around, it's going to require maximum effort. And there is another axis around which it's going to require minimum effort, minimum moment. And so the one that gives you minimum second moment is the axis that we're looking for. Okay, so we want to find this orientation. We're going to set up the problem and then show how it can be determined. So the second moment itself, we're going to define as E, is the distance of each point on the object from some chosen axis, that's r, squared, integrated over the entire image. So that is the definition of second moment. Now, of course, this axis that I'm showing here is essentially an arbitrary axis. So you take every point and you find the distance of that point from the axis, that's r, you square it, integrate that over the entire image, and you have the second moment with respect to this axis. And we want to find the axis for which the second moment is minimum. So the question is, what equation do you want to use for the straight line or the axis? Well, the one that's often used is y equal to mx plus b. We don't like this for our purposes here because m goes from minus infinity to infinity. When we try to minimize this function later, we're going to run into issues in terms of singularities because of this issue. So we're going to use a different parameterization of the straight line. A more convenient one is this one right here, which is x sine theta minus y cosine theta plus rho equal to 0. Now here, theta is the angle between the axis, the line, and the horizontal axis. And so that can only go from 0 to 2 pi. And rho is the perpendicular distance, the distance from the line to the origin. That's rho right here. And rho has to be finite because after all, the object lies in the image and therefore the axis lies in the image, and so that has to be finite. So both rho and theta are finite here. So our goal here is to find rho and theta that minimize E, which is the second moment, for any given binary image. We're assuming, of course, that there's only one object in the binary image. So let's take a look at R, this distance right here. This is a math primer. It's just a general concept here. Let's say you're given a line ax plus by plus c equal to 0. Then the distance of a point xy from the line R is ax plus by plus c divided by square root of a squared plus b squared. The absolute of that is the distance. And so now we can use our straight line equation, which is x sine theta minus y cosine theta plus rho equal to 0, plug that in there, a, b, c corresponding to that in there, and you get this expression. And now you see that in the denominator you have sine squared theta plus cosine squared theta, which we know is 1, and therefore you get r equal to this expression, where you see that this is nothing but the left-hand side of the straight line equation itself. So you plug in any x and y here, you end up getting the distance r. So we're going to take this, because now we have an expression for r that's in terms of theta and rho. We're going to plug it back into this equation, which is for the second moment, and you get this. You get the double integral of r, this is r right here, squared b dx dy. And now, remember, our goal is to find the theta and the rho for which E is minimum. So we're going to find the derivative of E with respect to rho and set it equal to 0. And when you do that, you simply take the derivative inside, apply it, set it equal to 0. When you look at that expression, you write it out and look at it, you get a very simple expression, which is the area multiplied by all of this, and all of this is nothing but x bar sine theta minus y bar cosine theta plus rho equal to 0. So it turns out, because we know that A is not 0, I mean otherwise the binary image would be 0 everywhere. A is not 0, you know that this is equal to 0, and here remember that x bar and y bar are the center of the area. The x bar and y bar are the center of the area that we computed earlier. So this tells us that whatever this axis is that corresponds to the least second moment, that axis must pass through the center of the object, x bar, y bar. So that's interesting. So what we do is that we simply move the coordinate frame, we change the coordinate frame so that we shift it so it lies at the center. So you can define x prime as x minus x bar, y prime as y minus y bar. You substitute those in the straight line equation, you get this, and you substitute that in the equation for E, which is the second moment, you get this very simple expression where A, B, and C are constants. And these constants correspond to these double integrals shown here. They can all be easily computed from an image. Here you have, with A, you have x squared, x prime squared, which means it's the moment about the y-axis. Here you have y prime squared about the x-axis, the second moment, and this is called the cross term or the product moment right here, x prime, y prime. So A, B, and C are easy to compute given any image. You just integrate over the image all of these different expressions. You get A, B, C, you plug that in here, you get a simple expression for E. But we're not done, because we have to find theta. And so now you find the derivative of E with respect to theta and set that equal to 0. You get a very simple expression here in terms of A, B, C, and theta, and that gives us tan 2 theta is equal to B divided by A minus C. Simple expression. Now we have to be a little bit careful here. One might assume that you found theta, but it turns out that there are two values for theta, two solutions for theta that come out of this expression right here. And that's because tan 2 theta is equal to tan 2 theta plus pi. What that means is that if you took this expression right here and you multiplied the numerator and denominator by -1, that still would give you the same value. And therefore, there are two solutions to theta. What does that mean geometrically? Take a look at this triangle right here. Here you have a minus c as the base and b as the height. And so you have tan 2 theta is equal to b divided by a minus c. That's fine. But now if you take 2 theta plus pi, this right here, and you form this triangle, which is like a reflection of this triangle right here, you see that now if you use c minus a and minus b, you still get tan 2 theta. So tan 2 theta is equal to tan 2 theta plus pi, and so there are two solutions for theta. So why do you have two solutions? Well, it's because one solution maximizes E and the other one minimizes E. We, of course, are interested in the minimum. So you have theta 1, which is half of 2 theta. That's one solution. And half of 2 theta plus pi is the other solution. And so these two are actually perpendicular to each other. So this tells you something interesting, that the minimum inertia, axis of minimum inertia, is going to be perpendicular to the axis of maximum inertia. And we need to find the axis of minimum inertia. So what do? Well, we know how to do this. We take the second derivative of E with respect to theta. And when the second derivative of E is greater than 0, we know that we have found the minimum. And the theta for which it is less than 0 is the maximum. So you substitute theta 1 and theta 2, your two solutions in there, and you see that indeed for theta 1, it's greater than 0, the second derivative. So that is the solution we're looking for, and the other one is the maximum. And finally, we have our orientation. We can find the orientation which corresponds to theta 1, the axis of minimum second moment. Okay. So this also allows us to figure out how rounded an object is. So remember that now we have E min and E max, the maximum moment, second moment, and the minimum second moment. The ratio of E min to E max can be used as a measure of the roundedness of the object. If you have a very thin object such as this one, assume that this is your object, a very thin object, you're going to have a very low value for roundedness because E min is going to be very small and E max is going to be much larger. If you have a rounded object such as this one, which interestingly looks like the one in the slide, you're going to have a larger value for roundedness. Now let's take a look at a few examples here. You have three images of three different objects here, grayscale images. You threshold them to get your binary images, and then you can compute the center of each object, which is a red dot that you see here. See that the center of the disk is exactly at the center of the disk. And then you have the axis of minimum second moment, which is this or this. And you don't have such an axis in the case of the disk, and the reason is that there is no axis of minimum second moment in this case. Any axis you pick through the center is going to give you the same second moment. In terms of roundedness, this is of course least rounded, a little bit more rounded, and then perfectly rounded. That's 1. So let's think about what we've done thus far. We've been able to take a binary image of an object, compute its location, compute its area, its two moments, minimum and maximum second moments. And so the area and the minimum second moment and the maximum second moment are features that you can use because these three features will not change as the object translates and rotates around. So you can use those to figure out, to distinguish between a set of objects. Very crude, but very effective at times. And then the position and the orientation, that is the red dot and the axis, is the information that you would choose, for instance, to program a robot to go and pick up the object. Now, we know that binary images are discrete in our case. We're going to take a discrete image and then we're going to binarize it, threshold it. Here's a discrete binary image. So you see these cells here. Each cell is a pixel. A pixel is either a 1, has either a 1 or a 0 in it. And here you use I and j as your spatial parameters. So bij is a value at a pixel in the row I and column j. And let's assume that the area of the pixel is 1. If the area of a pixel is 1, the total area of the object is just the sum of all pixel values, which is A right here. And you can now compute the center of the area, which is just I times bij over the entire image, sum divided by the area, and the same with y, so you get x bar and y bar. And finally, we can also compute the second moments very easily. Even if you don't change the coordinate system to the center of the object, you can simply go in there and use the origin itself of the image and essentially compute these second moments, A prime, B prime, and C prime, where you have I squared B, you have IJB, and J squared B. And from A prime, B prime, and C prime, you can always compute A, B, and C, which are the moments with respect to the center of the object. It's a very simple expression here, like if you write the expression for the moment with respect to the center and you expand it out, you can see that you can be expressed in terms of A prime, X bar, and A, and therefore all you need to do is to find A prime, B prime, C prime, and you can then find A, B, and C as well. So the reason we find A prime, B prime, and C prime here, that is, we haven't shifted the coordinate frame to the center, is you can imagine that an image is captured and you're doing your A to D conversion, you're reading out the image, and for each pixel, you can update all the moments that you were looking at. The area, the center, X bar, Y bar, that's the first moment, and the second moments can all be updated as you're reading out the pixels in hardware itself. You don't have to wait to compute the first moment, the location first, and then change the coordinate frame. You can just compute all of this. So by the time the image has been read out, everything that you want to compute in terms of a property from the image has been computed.